Okay, hello class. Evolutionary optimization. So I'm going to share the screen and we'll start with a little slideshow here. Okay, so evolutionary optimization, it's based on evolution. So we're going to use the same process. And this is actually a colleague of mine, Catherine Peating's children. She studied evolutionary optimization as part of her thesis, and she now does research in this area. So we're going to have these terms we're going to be using a lot. Same things that you would think of with respect to evolution. So it's going to be pretty natural to apply these techniques to many, many problems. And you're going to have to do that with your team at the end. So this will be one of these weeks where it's really learning by doing. I'll give you a sketch because I don't want to give away how to do each of your individual team problems. But we'll see that there's you'll have a choice of 5 or 6 different problems that you've seen before, like linear systems. I'm trying to choose things that we all have common background, Markov chains that we did this semester, how to solve the stationary vector, least squares problems, Sudoku problems for the folks that had last semester, the traveling salesperson problem. So classic problems that are easy to state, and some of those are notoriously hard to solve. We have other methods for solving each of those, but we want to practice solving them with evolutionary optimization to learn the technique. So this is a great way to do it. And so when you're doing these projects, you're often going to be coming back to with your team members and saying, okay, what does it mean to be a member of the population for this particular problem? What does it mean to be mating? What does it mean to be an offspring? So let's talk about those. We're going to talk about this through the framework of a problem that I worked on that with Catherine. We spent many years thinking about ranking problems and how to optimally do that. And so we define this thing called a hillside form. In the next couple of slides, I'll explain what that has to do with ranking. But a matrix, we're going to always be talking about square matrices. And it's going to be something called, which we defined as perfect hillside form. If it looks like this, the numbers in the rows are ascending and then the columns are descending, and it has zeros along the lower triangular. Okay, once we had that definition, you could also look at this as a city plot, and that's the phrase in MATLAB, and it's got this hillside form down here, right? Sloped form. Now, what does this have to do with ranking? Well, we started thinking about much of our data it's very easy to get data from sports. So let's just take one for the college basketball season, right? Can we take the college basketball season and put it in perfect hillside form? If we can, then we know that we have what's called a perfect ranking. It was a perfect season. The first place team beats all the other teams, and by increasing amounts. The second place team beats the third and fourth place, and so on. And then it's very easy to see what the ranking is. It's team number 1 is first place, team number 2 is second place, and so on. There's no debate about that. So our goal with the matrix that we're given is we want to symmetrically reorder the rows and columns. So if I produce a ranking, I'm going to apply that same ranking to both the rows and columns. And I want to force the matrix that I started with to be as close as possible to hillside form. And what happens then, we want to count the number of violations to hillside form. And this would be, there's many ways to have violations. You could have a upset, right? A lower ranked team went up and beat a higher ranked team. This would be appear as a non-zero in the lower triangular. Or you could just have what are called weak wins, when these entries really are not in the right order. And you can weight those different types of violations in different ways. So many, many ways to do this. So we'll just go with the vanilla version. Okay, so again, our goal then is to find, in the context of this problem, we can think of this as a permutation vector. Permutation vector is just a list of numbers. Those numbers, a permutation vector of length 1 is some ordering of the numbers in counting numbers from 1 to n. So a permutation vector of length 5 could be 1, 2, 3, 4, 5. It could be the reverse order, 5, 4, 3, 2, 1. It could be 1, 2, 4, 3, 5, right? So many different ways, n factorial different ways of arranging those n teams. And we want to find, of the n factorial, the one that minimizes the number of violations to hillside form. So it already kind of explodes with the n factorial, thinking about the problem this way to rank. Okay, this is a great slide. You'll probably come back to it often when you're trying to figure out your own team problem. What you want to do is start with an initial population. Move this thing out of the way. Okay, so we have some initial populations. Each one of these column vectors represents, we're going to just use a n=4 size problem. So we only have 4 teams to rank, and we're going to start by taking a permutation, and we can just do this out of the air at random. So give me a permutation vector. I can ask MATLAB or Python or R, whatever you're coding in. Give me another random one. Give me another one. Give me another. So we're going to collect 4 of those, and we're going to put those, each one as a column, and that'll be our population. And now the thing is to calculate the fitness. Okay, we haven't described that yet. The fitness is the measure of how good that member of the population does. And so let's take the first one, 2, 4, 1, 3. We would take 2, 4, 1, 3, 2, 4, 1, 3, and symmetrically reorder our data matrix for the season, who beat who, and what were the scores. And when we do that, then we go along and count how many violations we had according to our definition. So we'd say for this matrix AIJ, is AIJ less than AI plus 1, comma J, and we continue along in this manner, counting our violations. So each member of the population gets plugged into what it's like if you had last semester an objective function value, and that objective function value is a measure of the fitness. So each member of the population has an associated scalar score, its fitness score. And what we want to do is in evolutionary optimization is you want to keep the best ones and you want to mutate the worst ones. And so the mating process, there's lots of ways to do that. You're going to find a couple in the next few slides, but you also think for your particular problem. So the mating function could take 2 or more parents from the population member that were good, had good fitness scores, so in this case didn't have many violations, and create offspring. So in this example, we're mating the vector 2, 4, 1, 3 with 3, 2, 1, 4, producing this child that has similar properties, 2, 3, 1, 4. Mutating is what you do if there was a member of the population that was bad. It had a bad fitness score, a whole lot of violations over here. And you just want to randomly perturb it. You want to introduce some randomness to the system in the hopes that you could escape some local min and find something totally new. And there's lots of ways of doing mutations. We'll talk about some of those in the next few slides. Again, you're going to evaluate once you've created any new members. If the fitness is bad, it would look like this. If the fitness is good, it might look like this pictorially for our particular problem. You're going to take the ones that were good and push them into the population, removing any of the weak members of the population, replacing them with stronger members. If the fitness is bad, you can just discard it and move on. So every iteration is actually holding a population. So some number, in this case, 4 vectors it's holding in its population. It's calculating fitness for those. It's deciding what percent to mate, what percent to mutate. You can change that as you proceed. You might say, I want to always mate 50% of them, take all the good ones, and then all the remaining 50% mutate. Or maybe I only want to do 10% of them mutate. Or maybe throughout as the iterative algorithm proceeds, maybe I want to make this adaptive and mutate a lot in the beginning and then mate a lot at the end. All possibilities. Okay, and then the population in the beginning will probably be changing quite drastically. At the end, the population starts looking very similar. The members might be even repeats of each other, you might have duplicates, right? So if that's happening a lot or they're very similar, you want to say how much it's changing, then what you've done is you've converged at least to a local min and you print out the best. When you say I've had very little changes in so many iterations, I'm going to stop. That's my convergence criteria. Take the best one from the population at that point, and that is your final answer. Okay. Let's move on. Okay, so how do you create offspring? So lots of ways of doing it. It'll correspond to your particular problem. In this one with ranking, you can actually do you can take more than one parent. So this is P for parents. So we actually have 3 parents. And we can actually produce a child by doing something called the Borda count, which the Borda count is a way to rank average ranking vectors. So it's an average of these 3. It could be however many you want. So you can have sexual reproduction with 2, 3, 4, however many members you want. And you can do the mutating and think of that as asexual reproduction. Okay, so in this example, we took 3 parents. We did something called a Borda count. Look it up, but Borda count just says for each member, this is saying a ranking. Item 3 or team 3 is in first place, team 5 is in second place, team 4 is in third place. So these are positions, ranked positions in this vector. And then you find out for, now this is looking at team 1. So this is, don't be confused, this is a little bit different. This is now a rating vector rather than ranking. And the position here is team 1, team 2, team 3, team 4, team 5. So not rank positions, not first, second, third, but this is actually team 1. What I'm doing is I'm counting how many people did team 1 outrank. So here's team 1, last place, second to last place. So it only outranked 1 team. So we put a count there. That's the Borda count. This is from hundreds of years ago. Borda came up with this idea to rank average rankings. Okay, so then team 2, how many people did it outrank? 1, 2, 3, 4, 5. Total of 5. And we do that for all teams. So team 3 outranked 9 people, team 4, 7 people, team 5, 8 people. Then we sort this and we create a ranking vector then by sorting. So this says team 3 outranked the most people. It should be the first place position, 5, 4, 2, 1. And notice that 3, 5, 4, 2, 1 looks very similar. It's not actually a member of the parents that produced it. It's a little bit different, but it does share properties of all those. So that's a type of mating that takes 3 things, produces 1 child. Okay, another way you could do mating. So often you'll find for your particular problem, there's several choices. We want you to think about, discuss a couple, and then code at least 1. So here's another example of mating. This one takes 2 parents and does something called an average rank. So again, I'm trying to take good parents and produce a good child. And so I want to average them. And so you just actually literally average the numbers across the rows, sort this, and you get a child. So again, the child does share properties similar to the parents. That's what you're hoping. It's good news. Okay, but what if you had a bad parent and you want to remove them from the population? They got a low fitness score. In this particular example, we're going to do several different mutations, some really easy things where I could just do something called flipping. And you're literally making these up to make some randomness to the system. So I'm taking something that had a low score, and in this particular example, I'm going to flip. Oh, let me show you. Flip. So I've chose positions. What does it look like? 2 and 5 here. So I flipped the 2nd and the 5th positions, which happen to actually hold teams 5 and 2, and I flipped them. So I randomly picked 2 positions and I flipped what was in them. Another one, maybe you want to insert, is what we called this one. Let's see. Oh yeah, I took the 5 and just stuck it somewhere else. Take this 5 and jam it in down here, creates this new child. You can do lots of things, much more drastic. We called this one displace. What did we do here? I think we took a subset and pushed it somewhere else. So rather than just 1 item. Reversal, pick 2 positions, reverse everything in between those. So we picked these 3 positions, so a starting and an ending position, and flipped everything in between. Okay, so let's talk about this then. EO, pros and cons. You can handle large data sets with this. Often if it's a problem that can't be handled any other way, EO is a good place to start. And if you have enough randomization, there's proofs that you can eventually reach a global solution. But you need enough randomization, you need enough time. Sometimes that'll take a while. And it's a basic structure that can apply to so many different problems. It's just taking ideas of a population, they have fitness values, you mate and mutate, and you just keep doing that, iterating and iterating. It can be slow. You can get stuck in local optima. And because of randomization, identical runs will give you different solutions. So if you're trying to check your work, you may want to set the randomization at a particular seed, so you can do your code checking. Okay, now for you guys, what are your problems? So your team has to pick one of these and work on it. So do you want to think about a linear system and solve a linear system with an EO? Of course, there's many other ways of solving linear systems. In linear algebra, you learned Gaussian elimination. You may have learned LU factorization. You may have learned QR factorizations. There's so many different ways to solve these. But I want you to do it this time with an EO. So you have to think about, what is our fitness measure? If I had a random X, how would I decide if it is close to B? So think about that. How do I create a fitness function? How do I create members of the population, these vectors X? So you can assume you have an n by n non-singular matrix. I want you to, in your assignment this time, you have to demonstrate your problem, your code works on 3 problems that you can make up yourself of size 8. So we'd have an 8 by 8 matrix, make one that's non-singular so it has a solution, so you don't have to deal with that. So choose 3 non-singular matrices that you're gonna demonstrate your code on. Ways to get non-singular matrices, well, there's an entire gallery function in MATLAB, if you're using MATLAB, that you can look through. There's sorted named problems like Toeplitz matrices, Hadamard matrices. Choose ones that have the property that they're non-singular, or just pull out a textbook and make some, or just randomly make one, check that the rank is 8. Okay, so there you go. You're gonna get 3 examples and you're gonna code. A related one is the least square system. So you probably learned this in your stats class. We're going to do this time where A is a rectangular matrix. It's not square like it was in section 1, but make it full rank so that the least square system A transpose AX equals A transpose B. So very similar. You're back to a linear system. Make sure that A transpose A then is square and non-singular. That's what it means when you choose full rank. Okay, so you're going to generate an A, and then you're going to solve this system. Generate 3 A's that are going to make sure that this system is non-singular. And then you're going to march towards solutions. You got to figure out, what does a member of the population look like? How am I going to mate and mutate? How am I measuring fitness? And when am I stopping? Okay, another one we're all familiar with from this semester is the Markov stationary system. So we have this stationary vector. We know our stationary vector if we solve this. P is a stochastic matrix, so randomly generate ones. We were doing row stochastic, so the rows sum to 1. It has to be irreducible, so generate an 8 by 8 stochastic matrix, and you're going to start with some random stochastic vector. That's what members of the population have to be here. And then you want to make sure that when I multiply on the left, so pi transpose, pi is a column vector, so pi transpose times this matrix P gives me pi transpose. I know it's a stationary vector if it satisfies that. We're going to talk about job assignment with preferences in a moment. The traveling salesperson problem, classic problem. You have n equals 8 cities. They have distances between them. The traveling salesperson has to visit all cities and return home when the minimum amount of distance covered. Okay, so what would it mean to be a member of the population then? Another permutation vector where that represents the order of the cities that you're visiting. And then the problem we've spent a lot of time last semester with, Sudoku. Instead of n equals 8, you're just going to do 3 puzzles, which are 9 by 9 matrices there. Demonstrate that it works on that. Okay, so some things you should be asking yourself repeatedly through this, and you should be making up pseudocode, working by hand. So generating those 3 examples is the first place. And then you want to just work by hand. What do parents and offspring look like? What's a member of the population look like? Give me an example of that. What would it mean to be a member of the population for your particular problem? Sudoku, okay, it's an entire puzzle. What's the fitness value? What does it mean to be a good member? What does it mean to be a bad member of this particular population? How will you generate that? EO is classically used in optimization, and many times then you have a very explicit objective function. Like for instance, the traveling salesman problem can be written as an integer program. There is an objective function. You want to minimize the total distance traveled. So clear idea there for what the fitness function should be. Each permutation of the cities is associated with summing distances. That is your objective function. Right, so it's easy to get a fitness there. Other ones, it takes a little bit more turning your head sideways to figure out what is the fitness function, because it wasn't written as optimization. Like AX equals B wasn't written as an optimization problem. But you could think of it as how well I'm doing by maybe how close you fit something. Okay, I don't want to give away all the answers there. So let's move on. You have to discuss 3 mating and 3 mutating functions, and you code at least 1 mating and 1 mutating. So I don't need to see multiple ones unless you want to have bells and whistles, but you had at least thought and discuss them in your presentation and then show the code. How do you know when you're done? What's a stopping criteria for your particular problem? You again want to write out the pseudocode for this problem, and then you actually have to code it whatever language you want and demonstrate that it works on 3 examples of size 8. Okay, so one last thing, we'll show an example here on the whiteboard. Maybe I'll have to carry. Let's see. Oh yeah, I think you can see it a little bit. So behind me, I have what's it called, a job assignment problem. You're going to do an extension of this, a job assignment with preferences. So in the job assignment problem, you have this matrix of data. So we have workers on one side. Sorry, I can't zoom much closer, but I think this gives you the idea. You have workers and jobs. So this is going to be a square 5 by 5 matrix. So we have 5 workers, 5 jobs. And so you'll do an n equals 8 problem. These workers have jobs that they are capable of doing. So like worker 1 could handle job 2 or 3. They can't do 1, 4, and 5 because of the zeros. Worker 2 can only do job 2. Worker 3 can do anything, and so on, right? So this is their availability or their ability to do a particular job. Doesn't have any preferences there. You could imagine, rather than a binary matrix, maybe having integers 1, 2, 3 for their preferences of jobs that they can handle. You still could have zeros on things they couldn't do. For evolutionary optimization, though, instead of a matrix, I could think of writing this as a vector. This is a permutation vector. This means worker 1 gets assigned to job 1. Worker 2 gets assigned to job 2. Worker 3 gets assigned to job 5. Worker 4, and worker 5 to job 3. Now, this may not be a feasible assignment, though, so you'd have to go back and check, and this is somehow associated with the fitness value. So you want to figure out a way to look at this and calculate how fit it is. How many of those are actually feasible? Can worker 1 do job 1? No, so that doesn't get a score. 2 could do 2, so that's 1 point. 3 can do 5, 2 points. 4 could do 4, yes, and 5 could do 3, no, it can't. So maybe only 3 out of those 5 actually get, so we want to maximize in some way. So think about that with relationship to your fitness. So again, I don't want to give away all the problems, so just trying to sketch out for a couple different problems, ranking and job assignment. So that's a basic standard job assignment. You'll do a job assignment with preferences if you choose that one, and just how you think about the thought process of what it means to be a member of the population. And then because that one's also just a permutation vector, you can leverage off some of the ideas in the talk earlier to mate, mutate, and we talked about ideas for fitness. And there's usually not just one way to do all these. There's many ways to calculate fitness, to do mating and mutating, and then also think about what does it mean to be done with this problem that you've converged. Okay, I think that's it. It should be a fun week. So your team is going to, one last thing. Let's see, share the screen. We'll go to your file in Oaks. A couple things I put up here. So you have your assignment, descriptions of the projects, and then the PowerPoint that I just gave is right here. So let's go to your assignment this week. So you have to present next week, but it is a tough DIS presentation. This is important. Now that you've read, we want to polish this thing to, this is one of your other main graded presentations, so put a lot of effort into tough testing it. You're going to also submit your code and demonstrate that it works on 3 problems of size n equals 8. You just need one team member to email that to me. So it'll be the code that's been commented plus the input output for those 3 examples. And then individually, you're going to read the project descriptions. I'll go to that next for the remainder of the semester. So this is the last of our mini projects is EO. And I want you guys to read those and email me a list of your choices. What's your first choice for a project, second choice, third choice, along with a brief rationale. Again, the EO problems are listed again here. A great reference if you like EO, this is a wonderful book, How to Solve It, Modern Heuristics, and it focuses a lot on evolutionary optimization. All right, let's go back. So I know you're focusing on EO this week, but before next class, spend 30 minutes, an hour reading all of these 4 times through and deciding what are your preferences. So we have some projects from a colleague of mine, Dr. Tim Chartier at Davidson. He does a lot with Sports Analytics, super connected there, but he each year is asked, has just a flurry of interviews, radio, TV, social media stuff about March Madness. He's Mr. March Madness. And so he wants a support staff to help him. The project could include clustering, ranking, data scraping. There is a lot of data and code already available. He also is interested in Wordle. He's been asked to write a couple articles. He's sort of a popularizer of math about Wordle. And so some of the things that he's interested in are puzzle creation, puzzle solution methods, stats associated with all that, creation of extensions to the game, like that's a basic, but what would be extensions? And he's thinking of 10 or 15 years ago, I guess 15 or 20, when Sudoku first came out, it was a big craze, and Wordle has that same feel. We worked on some stuff on Sudoku. Again, a lot gets picked up in the media, so I think he's interested in, he has a lot of mathematical questions associated with this game, just the way he did with Sudoku. And so one of the things that often comes from that, like Sudoku now has all those variants, right? Like Samurai Sudoku and it's gazillion different variants. And so I think that might be a direction for Wordle. You could use a lot of your text frequency things that you've learned. Okay, and then there's a couple, the last 3 are all from industry, local industry. This will be a way to get foot in the door at one of these places. I know it definitely worked for Colin and Aaron who are at those places. So MSG stands for Mission Solutions Group. They've submitted 2 projects. Take a look at them. Pretty much ranking, I think, in the first one and lots of text mining in the second. And then Aaron has this one about health related data. So it's a little bit healthcare, but text mining with healthcare. You'd be working often with these contacts on those to get more descriptions. Okay, and then a few people have asked, do we have to use, I would prefer that we pick, each one of these is covered. So give me your preferences, but if there's a strong reason why you have something you're just absolutely attached to, you have to basically submit a proposal on why you want to put a number 6 in there. Okay, all right, have fun. It'll be a fun week with EO.